Guys, in this video I'll talk about transformers. Transformers are amazing devices which are very beneficial for us. You must have seen a transformer just in your society, and if you have somewhere visited a power station, then there's a very big transformer installed outside that. Okay, so what does transformer do? It works on the principle of mutual inductance. So it can't work on DC, as DC is a constant power supply or constant voltage supplier. So there will be no change in current or flux, so no EMF will be induced. And why it is used? It is used for regulating AC or stepping up or stepping down the voltage, which is very useful for power transmission without change in frequency. This should be without. Okay, without change in frequency. So how does it work? It is made up of two coils basically. The one is already made and I'm drawing the second one. This is called input or primary, from which power is supplied, and from which output is taken is called output or secondary. Output or secondary. Both are wrapped around the same core so that magnetic field, flux through each loop is same. Okay, so what we can assume, when no flux is leaked or no flux leakage is there, flux through secondary or primary, I'm talking about each loop, will be same, as they are made up of almost equal area and same field is passing through them. Okay, so d phi by dt, rate of change of flux in secondary, is nothing but EMF induced in secondary, and rate of change of flux change in primary is EMF induced in this. So what is this? D phi by dt is nothing but NBA, and the only thing that is changing is magnetic field, and the rate of change of magnetic field is same in both. So secondary EMF is number of turns in secondary, rate of change of field in secondary, which is same as primary, area, which is also same as primary. So these two terms will cancel and we are left with this. This is the basic equation of transformer, which is valid even if there are some power losses. Okay, so this equation is valid even non-ideal transformer. Okay, non-ideal transformer, this equation is valid. But if we assume that there are no power losses, we can say the power input, which is EMF induced in primary, or voltage input into current input, is current output into voltage output. Okay, so we can also say input and output power are same. So from this equation I can guess primary voltage by secondary voltage is secondary current. Just divide this and take it here, you will get I secondary by I primary. Please do write what I am saying. I have already written that because that is a theory portion. I am basically concerned with the numerical part, but this theory portion is quite important, so write everything what I am saying. So number of turns in primary to secondary, this was the initial equation which is valid in this. Okay, so the ratio of current will come into picture only when we can assume that there are no power losses. Otherwise only this is valid, this is not. If power losses will take place, we cannot use the ratio of currents also. Okay, so power is transmitted at a very high voltage to avoid losses and theft. I will explain it further with the help of an example. So this is a power station which is generating power at 110 volt. So we have to send it to a very large distance. Sometimes that distance is from one country to another country. Okay, so we have to send it at a very high voltage, which is 22,000 volt. Okay, 110 the power is produced and we have to send it at 22,000 volts, so we need a step up transformer which increases the voltage to this. But this voltage is very dangerous and can't be used in our household supplies, so we need a step down transformer which is just placed outside our society, so it steps it down to 220 volts, and these are our houses. Okay, don't get emotional with my drawing. Okay, this is just to explain things. So no moving component is there in transformer, hence there are very minimum mechanical losses are there, or we can say no mechanical losses are there. So loss due to eddy current, hysteresis and joule heating is the main cause of losses in transformer. Okay, in this question there is a town which needs 1100 kilowatt at 220 volt, and it is 20 kilometer from the power station. Okay, so we need the output power, that is the town needs, so this should be the output. And station is generating power at 440. Power is transferred at 220 kilovolt through this wires to 2200 volts. So each kilometer has a resistance of half ohm. We have to find the current through transmission wire and losses. Okay, so we are assuming that the transformers are ideal. Losses takes place only through transmission or transmitting wires. So current through transmission is nothing but power output into power output is nothing but V output into I output. So how much power is required? That is 1100 kilowatt at how much voltage? 220 volt. So the current is nothing but divided by this, we get 5000 ampere. And just by equating how much resistance is there, resistance will be 20 kilometer. This half ohm per kilometer is 20 into half, that is 10 ohm. 10 ohm. And I square R, I will say 5 into 10 to the power 3 square into R, which is 10. How much power is lost? We can say 25 into 10 to the power 7 watt power is lost. Okay, so there is a slight mistake I made. The power is transferred at 220 kilovolt. Okay, the power is transferred at 220 kilovolt, so this will be 2200 into kilo 10 to the power 3. So the current will nothing be how much? This will be half 10 to the power 3, so current will be 0.5 ampere. And when we equate it from I square R, we will get how much? 0.25 into 10, 2.5 watt will be the loss. Okay, that is the reason why we transfer or power is transferred at very high voltage, because of very small current in the transmission wire, and because of that there are very small joule heating or losses due to transmission. What is the power produced by station? Okay, as this power is lost and this power is required, so the power produced is nothing but 1100 kilowatt plus power loss, which is 2.5. more than that, that is negligible. So we can say almost all power is transferred. This is kilowatt and this is watt, so 1100 kilowatt is this plus 2.5 watt is negligible. And current through the station, so we can say power generating at station is at this much volt, so we are neglecting this 2.5 watt, which is the loss. So power through station is nothing but voltage at station into current through station. Power we know 1100 kilowatt and the voltage across station is 440. So we can easily say that will be 1 by 4, 10,000 by 4 will give you how much current? 2.5 kilo ampere current will be generated through the station. What about number of primary, number of secondary? That is at station. So at station, what is doing? 440 is the input and 2200 kilowatt is the output. So we can say number of primary to number of secondary is EMF primary to EMF secondary, which is 440 by 2200 into 10 to the power 3 will be in the denominator. So we get around 10 to the power minus 3 by 5. In the next part, number of primary to number of secondary at society. Society input is 2200 kilovolt and household supply is 220. So that should be the output. And number of primary to number of secondary is E primary, which is 2200 into 10 to the power 3 by 220. So that is 10 to the power 4. Okay. Enjoy.